Can you guys see the paper?
Yeah.
Okay, great. So I was between presenting two papers this week. One was this paper called ClimSim, which and another one which is called GenCast. So ClimSim is one of the papers that got an award at NeurIPS last year in December. And then GenCast, and it's about climate simulation. And then GenCast is about weather prediction, and it came out of DeepMind, I think, like a month or two ago. So there's been some cool stuff on the climate simulation and weather prediction. One thing that was made clear to me by reading this paper, though, is that they're actually different problems, the two of them, climate simulation and weather prediction, because climate simulation is basically trying to model like the entire world and like these like in terms of summary statistics of its climate at different grid points, whereas weather prediction would focus more on like a local area, and they would try to predict different phenomena. Like this paper is really trying to predict like the changes in temperature and moisture and stuff like that happens that's like happening at a macro scale on the planet. So yeah, this paper is and then what this paper is doing is introducing a new data set, and because of that, a new problem to the ML community. I think that's one of the main reasons why I got an award, because I always think that like introducing a new problem is a very valuable thing to do. Like when you introduce a new problem for people in ML to do research on, because I do think that sometimes we in the ML community end up like focusing on problems that we have data sets for and like researching them to death. But when you get a new one, that means that there's something new to research and a new way to make a contribution. But usually when a new problem is introduced, a lot of the time there's not a data set available for it, or not a very good one. But here, I mean, in terms of what they want to do, they've introduced a really good data set for it. So I think it's a really good contribution. You can see how hard it was to collect this data set given the number of authors. Although there's only one corresponding author, so I was wondering why there's so many people here. Not exactly sure. But like, how do I start this? Well, let's talk about what problem they're trying to solve with this data set. So the overall problem is simulating the climate of the world, of Earth, or additionally other planets if we ever go into space, with the idea of being able to forecast forward how the climate is going to change, in part to deal with to understand climate change, and just in part to be able to predict the weather in the future. But the problem with these simulations, or the difficulty of these simulations, is that they're very compute intensive. There's like very complex physics that is occurring. Like, you know, I don't know if you guys have ever heard the joke that there's like a joke that I think Einstein says which is like something along the lines of, when I die and go to heaven, I think it's go to heaven. There's two things I don't know, like the solution to the Navier-Stokes equation, and then like the solution to unifying quantum physics and relativity, something like that. And he says, when I die and go to heaven, I'm hoping that I'll be able to find out the answer to the second one, because he believes that like the Navier-Stokes equation, which governs fluid flow, is just like even a mystery to God. That's the whole good joke of that. And that's like one of the types of equations that governs the physics around climate change. I mean, around simulating the climate. So it's really complicated physics. And the way that we end up dealing with it is by discretizing whatever space we're trying to perform the simulation on, and then doing some level of something like a finite element analysis, or basically trying to model like the interdependencies between the nodes and do time step based changing calculations of change. And this is really computationally intense, especially as the resolution of the model increases. So they say over here that like current climate simulators, like the ones that we use to predict the weather, to do studies about climate change, have their typical smallest resolution is of the order of 80 to 200 kilometers. But two things that they say over here is that like, where is it? It's basically, they say that cloud formation and rainfall are very important physical phenomenons to model if you want to be able to model climate accurately. Oh yeah, here it is. Current climate simulators poorly represent cloud and extreme rainfall physics. However, in order to do that, you need to represent cloud formation. Like to represent cloud formations, you need to have a resolution which is 100 meters or finer. So they're saying that means that to be able to like really accurately estimate the climate or forecast for the climate, they need to decrease the order of the resolution of their increase the resolution of their model by 6 orders of magnitude, which you can imagine probably like, there's probably some kind of like quadratic law with the amount of increase in compute that you have when doing that or something along those lines. So it's just a really hard problem in terms of compute. And the hard part of it is like, there's physics that you can almost treat as local physics, like to a specific area, that will influence the way that the variables related to climate change in that area. And simulating that local physics is one of the main computational constraints of these models. So what they want to do, or what the problem that okay, so we've talked about like, there's a couple of solutions to this problem of like modeling this small scale physics. One of them, they say, is like create a uniformly high resolution simulator, which means that you uniform in this case just means the grid size is the same everywhere and treated everywhere in the simulation. And so they're saying like, okay, what if we made a grid simulation that's 100 meters in resolution? Well, you can't do that with the computers that we have today. So you need to model it with something that saves on compute. So there's one solution would be to like train ML models to just and be able to do like a forward pass to measure to determine the change at every resolution at that resolution. But it's very, very expensive to collect data because of the compute costs of doing that for that resolution. And also, I actually think that's what they're saying. Yeah, it's just really hard to collect data when you do these really high resolutions tests, and you wouldn't be able to do it for a long period of time. So they're saying, okay, we're not gonna focus on that as the approach that we want to use to improve our climate simulators. Instead, to make them more compute efficient, what we're going to do is we're going to create a multi-scale climate simulation method. And what we're going to do is we're going to have like a coarse scale where we actually use a physics model to perform the simulation. But at every time step, what we'll do is we'll query an ML model that will tell us like how this local physics has affected the variables that we care about, and we'll feed that into the coarser simulation. So it would be like a hybrid approach using the physics model at the coarse level, and then at the At the more fine-grained level, you would use an ML model instead of using an additional simulation. Because basically what happens right now is like the way that they collected data is they use a weather forecasting system that's I think it's yeah, that's maintained by the Department of Energy. It's called, where is it? E3SM MMF. So they use this model, and the way it works now is that it actually it has a coarse-grained simulation of the entire planet, and then for each grid, it discretizes the entire planet into grid points, and then for each grid point, it has besides having this large-scale physics simulation, there's a small-scale physics simulation that occurs at every grid point to get the correct like local physics impact, and that's how this simulator works. But we want to ideally replace that small scale physics simulation with some kind of ML model. So that's kind of the whole problem. It's like we want to be able to simulate the climate at a finer resolution, but we can't because it's too compute intensive. So we're going to focus on multi-scale climate simulations and try to replace the smaller scale simulation with a ML model. And so we're going to create a data set for that problem. Let's see. Skipped over. There's another thing that motivates the problem is that often what physicists or scientists will do to deal with the fact that these small scale simulations in a multi-scale problem are expensive in terms of compute is they'll make like closed form equations, which they call parametrizations, to say like based on empirical observations to model this small scale physics. But they say, like, unfortunately, assumptions in these parametrizations often lead to errors that can grow into inaccuracies in future predicted climate. So there's also this approach of creating like closed form equations, but that doesn't, based on empirical observations, but that doesn't seem to be very good because I guess like small flaws in the assumptions can propagate a lot when you're doing these climate simulations. Like that. Like that. Okay, yeah. So they're just saying that they're creating this data set. One thing that they do say somewhere over here, but I can't see where I highlighted it, is that they also, like, the good thing about this data set is that it's if we create models for emulating the small scale physics, they should be compatible with like the simulations that we use in like on a day-to-day basis to predict the weather and the climate, because but yeah, that's like one of the benefits of the data set, and I think that's because of what I said before, that they're using like a climate simulator that's maintained by the Department of Energy, and there's another reason somewhere else that I'm sure I'll pass by at some point. Okay. So yeah, one of the reasons why I chose this paper was I was hoping to learn a little bit more about weather forecasting. So let's go through some weather forecasting terminology and stuff. So in terms of atmospheric science, convection refers to storm clouds, rain development, as well as associated turbulent air motions. So convection is different from convection in general physics here. It's a couple of different phenomena. And it says convective parameterization represents the integrated effects of these processes, such as vertical transport of heat, moisture, and momentum within the atmosphere, and condensation and heating and drying. So it's really these things that they're trying to emulate, which are hard to emulate. And the things that they're trying to predict are like vertical transport and heat and moisture and momentum. So these are like you can kind of, I think this is a good example of the difference between predicting the weather and predicting the climate, because the weather would try to predict like storm clouds or rain development, but predicting the climate is more about predicting these variables like vertical transport of heat and moisture and momentum. And in fact, they don't actually predict storm cloud, rain development, and all this stuff. They try to overstep that with this approach. Yeah, nothing there. We talked about that. Okay, and I guess another motivation for this is that current climate simulators, in climate simulation, changes in precipitation with warming is a particularly important issue. So this is just saying like, basically as the climate increases in temperature, being able to predict the amount of like rainfall is very important. You can see that because like, basically it's an important issue in climate change, and it can cause, if like the earth warms enough and we can't predict like maybe very extreme weather events that are going to happen because of climate change, that could cause a lot of, it could lead to a lot more damage than if we were able to. And so it says that current climate simulators agree with the direction of this change. So they can say like whether precipitation is going to increase or decrease, but they can't agree. There's like a huge spread in the quantitative rate of increase with the warming. So, you know, motivating this from the perspective of like basically predicting natural disaster to mitigate the damage that's caused by climate change. Okay. Okay, some interesting other earth science stuff if you guys want to know about it. So there's a lot of climate simulations that are simpler than the ones that we use on Earth, and they're simpler because they're done on aqua planets. So I didn't know this, but like a lot of the climate simulation research will just, I think, just model a planet as just water, because the interaction between land and water is, I guess, very complex. I was wondering why there are always water planets and not just oh, I guess if it's only land, maybe there's no water, and then yeah, so much. It seems like so much of like predicting the climate has to do with predicting like macro properties of like water in the atmosphere. And so they're saying like most of work that's done like hybrid ML emulators have focused on simple aquaplanets, and then there's some that have included real geography, but none that like model the full coupling between land surface and I guess the ocean and then what's above it. They talk about some of the architectures that's been used, some other stuff, not super important. Okay. And then they do mention all the way down here in the related work, they're talking about like non-multi-scale setting here. So where you're using ML to predict the weather completely. And they say, for instance, it has been shown that incorporating spherical geometry and resolution invariance through spherical Fourier neural operators leads to stability of rollouts, long rollouts. So they're talking about some interesting stuff that's happening in ML to measure the climate, to predict the climate, but they don't really touch on it here. And actually, one thing that I found really interesting, and I was wondering if it's a limitation, not a limitation, I was like, why do they do it this way, is how they treat 3D coordinates and even 4D when you consider space in the data set and in their experiments. So we'll come back to that later, because for example, the way that they treat the data set, you couldn't incorporate spherical geometry into the problem. You'd have to transform the data set in order to incorporate spherical geometry. It wouldn't be too hard, but I was like, oh, why aren't they doing that in their set of experiments to create baselines? Okay, a little bit related work. Okay, so let's talk about the actual data set that they constructed. First, I'll talk about how it was collected, and then I'll talk about what's in it. So they used A100s for a total of almost 10,000 hours. They collected climate data at 20-minute intervals for 10 years. So that's like, they say it a little bit farther down, 72 time steps a day, 10 years worth of days. And they use they have three data sets that they collect. Two of them are, I think, of the Earth. And they use what's called a cubed sphere horizontal grid, which, let me bring it up, because I was like, I also, let me see. I was wondering what that is. So basically, for those who don't know, a cubed sphere grid looks like this, and it's when you impose a cube geometry onto a sphere, and then maybe that means that you can like treat the sphere like a cube. I was thinking probably that's why you do it, because it simplifies the math a lot for calculating the interdependency between points. But so they use an unstructured cubed sphere horizontal grid with 21,600 grid columns. So I've shown you the cubed sphere part, but the other part of it is that they're using what they call an unstructured grid, which I didn't look up, but they explain it a little bit. And basically in an unstructured grid, every horizontal location has a single dimension to show, say, location. So even though this is a 2D surface that they're like the surface of a sphere that they're modeling, they're not using two coordinates to model it. They're using a single column for their unstructured for the grid that they're using, which maybe again makes the computations a lot more efficient when you're simulating. I don't know why they did it this way, but this was interesting to me, that they're using an unstructured cube sphere horizontal grid to model the surface of the Earth. It's got a lot of squares, but I think that's still like, I don't know what size it. Oh, they say this is an approximate grid spacing of 1.5 degrees. Yeah. They actually do say here, but unlike a traditional climate model that maps points across the sphere using 2 dimensions aligned with the cardinal north-south, east-west directions, unstructured grids use a single dimension to organize the horizontal location of points. So I wonder, I wish I could ask the author, why did you use a horizontal unstructured grid? But we can't.
Does it also mean that the grid sort of, it should wrap around itself, right? That if I go along this grid in one direction, I should sort of end up at the other end again, no?
That's probably true.
Yeah, it's quite interesting how they would handle that in the data, right? That you do have this sort of wraparound symmetry.
But I was wondering, but you wouldn't be able to tell, at least from the dimension with a single number, like which all of the adjacent grid spaces to you. That's what I was thinking, at least with this unstructured grid. So I was like, that you'd have, if you wanted to somehow treat the problem as like on a more global level, you couldn't. Although one thing that I was thinking about this is, so okay, let's talk about the problem. I'll go back to what I was thinking about. So the data set that they are collecting, it's made of input-output vectors. The input vector is a dimensionality of 124, and the output vector has a dimensionality of 128. There's actually two versions of this, because this is not completely true. This is like the simplified problem. There's another problem. There's the data set, actually, the input size is 617 variables, and the output size is 368. But for the purposes of experiments, I think they just used these 124 and 128. So these are just input-output pairs of vectors. And the input is basically like at a specific time step all these macro scale climate variables. And the output is the output of the same variables plus some other stuff after you've taken into account the local physics with some kind of simulator, with a simulation of like that local physics. And so you're using the ML model to predict that the impact of the local physics. So I was thinking, if you're using an ML model to do that, then maybe you don't need to know about adjacent grid spaces, because the computation that was done to get the output didn't take into account information from any of the other grid spaces. So maybe it's not that important that they're using an unstructured horizontal grid.
So, sorry to interrupt. The ML step would then sort of be to replace the physics simulation with something that looks similar enough, but it's just a forward pass.
Yeah, exactly.
Gotcha. Thank you.
Most of the maybe some other details. Most of the dimensionality of this comes from the fact that you have, like, you can see it over here. So there's actually only, I think it's in the supplemental material. It's something like, oh no, it's not. It's yeah, okay. There's 24 2D variables and 10 3D variables, but this is of size 120. The input is of size 124. And so a 3D variable is a variable that changes with respect to like the height into the atmosphere that you are. And that's what I think they're showing with these, like these blue and red over here in this figure. They're using 60 vertical levels. So they separate the 3D aspect of estimating climate into 60 levels. And so there's 24 variables which don't vary across across height, and there's 10 variables that do, and you can see some of them. They're like temperature, specific humidity, surface pressure, I'm guessing doesn't change with height, solar insolation, etc. And then the output is similar, trying to predict like the changes in things, heating tendency, so how the temperature is going to change, moistening tendency, how the humidity is going to change, and so on. So that's the data set. Fairly simple, and as from the perspective of an ML problem. It's really just, I think it's basically seeing if we can create a model that can replicate this, can approximate this small scale physics. I was even wondering like how much innovation we can incorporate from ML into this problem, or it's just going to be like I don't think a transformer would be useful here, because that's not a model that they tested. But like, what can they throw at this problem to make it, besides what they did in their baselines, to improve on it? I'll be interested to see what comes out of this, because it's literally the structure. There's not a lot of structure in this data that they could exploit. It's like just input-output pairs that are vectors. In terms of experiments, they took the 10-year data and they used the first 8 years as training, and then the last 2 years as test. And they left a 1 month gap, or to make sure that like the model, there's no training set leakage based on temporal correlation. So they're basically saying, if you can't see how the climate is looking for a month, then you won't be able to. There's no correlation between the climate to month before and after a certain point, or maybe there's very little. They talk a little bit about energy usage. Okay, let's talk about the pre-processing that they did for experiments. So all the experiments, they're just trying to create a baseline for future work. So they're a little bit different than, I think, if someone was trying to write a paper where they're trying to solve this problem. They're just trying to create like some initial steps, and they do some interesting pre-processing. For one thing, they collapse the horizontal location and time into a single dimension. So they're taking their unstructured single-dimensional grid of a two-dimensional surface, and then they add time to it, and they make it into a single dimension. So they've collapsed 3 dimensions into 1. They normalize all the variables by subtracting the mean and dividing by the range. Yeah, some stuff that's not super important. They do, yeah, some stuff that's not super important. Okay, so the big thing for me is that they collapsed they basically took out time and put it into the horizontal grid, into their 1D grid. Their baselines are a CNN, an encoder decoder, some kind of regularized MLP. I don't know what it means to regularize an MLP, but it outputs a mean and a standard deviation. An MLP, a randomized prior network, which is an ensemble of MLPs. And they said that they had to resort to data bootstrapping in order to mitigate the uncertainty collapse of the ensemble model when tested beyond the training points. So basically the model just kind of fails unless you do this data bootstrapping outside of the training set in terms of the grid variable. And then a conditional variational autoencoder, which is just a variational autoencoder where you're not training the model to do reconstruction, you're training it to, the output of the model is different than the input of the model. So these are the 6 networks that they chose as baselines. And they report results here. It seems there's like clear winners in terms of best performance. They're the CNN and the MLP. The CNN, by the way, it's a one-dimensional CNN, so it's basically only going to be looking for relationships across the vector, so across the z dimension of the problem, which is the height dimension. So yeah, it seems like the CNN is better at estimating changes in temperature and I think humidity. And then the MLP is better at all these other things. Snow rate, downward surface, long wave flux, stuff I don't know that much about. They measured 2 things, mean absolute error, so the error between the actual value and the predicted value, and then R squared, which is the coefficient of determination, which I looked up. Could bring it up. We can bring it up, so because it's probably easier to. It's a metric I have never used before. So basically, you'll see it over here. It's saying the coefficient of determination is the proportion of the variation in the dependent variable that is predictable from the independent variable. So how much of the variation in terms of what you predict is predictable based on like what you see in the data, basically. So if you have the best value you can get for a coefficient of determination is 1, and the worst is 0. And it's let's see, what is it saying? If you have 0, it means that your model is like perfectly calculating the correct answer at for every time set, for every value. I mean, if you have 1, if your value is 1, if it's 0, it means that your model is about as wrong as like the variation you see. So like in that variable, if you just calculated the variance in the data, and -1 means it's worse. So if we look back over here, you can see like for CC, which is rain rate, every single model except for the CNN has a negative determination of coefficient of determination, which means it would have been better to just like fit a flat distribution on that variable and sample from it, unless you're using a CNN. So yeah, these are just some baselines that someone who wants to do future research on can point to these statistics when they're trying to figure out if their model is better or not. They did an experiment where they used the full input-output data set, and they found that the model actually performs better in terms of predicting things they care about when you're doing it on the full input-output data set instead of just using the concatenated vectors, the shortened vectors, the truncated vectors that they were using. We talked about results. The only other thing that they talked about here is that for different for different properties that you're trying to predict, they can have a different error rate based on like the height above the earth that you're at. So it seems that like I think MLPs are better at predicting like lower level. They have a much better we'll read it up here. It says R squared, the coefficient of determination reveals that architectures, these architectures consistently perform better in the upper atmosphere, whereas the highly optimized MLP model performs better in the lower atmosphere. So for some reason, different models perform better at different points in the atmosphere. Maybe that means that like in the lower atmosphere, there's not as much uncertainty in terms of correlation between variables than there is in the upper atmosphere. I don't know. One thing that, like this observation that they make here, I was thinking what's missing is for them to tell us what does the physics say about these relationships in terms of the variables at different points in the atmosphere. So we know the physics that we're using to simulate to gather the data. So that means we know the relationships that we're simulating that produce these input-output pairs. So at least based on maybe the physics is too complicated, but if it's not, then you could say like, okay, well, in the upper atmosphere, the relationship between rain rate and like across levels is this. So it makes sense that this model would perform better because of this inductive bias. And there's none of that here. So I was wondering why there isn't any of that here, since we know the physics that generated those input-output pairs. It's not like a lot of ML problems where we don't know what the underlying equations were. And that comment is one that I was thinking, it was also true for me when I was thinking about this, where it says, a systematic and quantitative pruning of the input vectors based on objectively assessing. So this is talking just about these are like, this section, sorry, 4.5, we've just gone through the results kind of. It's talking about like it's basically like pro tips if you want to work on this problem. And one of them is a systematic and quantitative pruning of the input vector based on objectively assessed causal relationships to the subsets of the target vectors has been proposed in an attractive pre-processing strategy. So they're basically saying like for each target feature you want to predict, it would be great to do some like causal analysis to figure out what's related to it. And again, I was thinking, I mean, if we know the physics, then don't we know the causal relationships of what affects what? Like why do we need to do some kind of analysis to do it? Like why is this suggested as a pro tip if we know the physics already of this input-output pair? So I didn't understand that part of it, like why there wasn't some parts of the paper saying like this is the physics, this is what these are the relationships. Do what you will to encode them into the problem without making without replicating or like while still maintaining compute efficiency.
I think the problem there can be the interactivity between components. Right? So especially with climate, your feedback loops. Say you have the the heat reservoir of the oceans, which is massive, interacting with other heat reservoirs on such scales where there's a lot of chaotic behavior in the sense that very small differences can make a very large effect, and it becomes very hard actually to say which one is the root cause. As an example, I think the interesting one was the CO2 lead to the end of the last ice age, right? And actually it's rather difficult to show that actually there was an increase in CO2 that actually then say brought on a cascade that actually sort of ramped up the heating by changing some buffer values, and so it's unfortunately not that straightforward.
Okay, that's probably, so the physics is just too complex to be able to do that type of analysis, essentially.
Possibly and potentially even unknown, right? So it's these kind of things you have. If you think about how it was only fairly recently, right, that they found out that that when they have these big oil tankers or big tankers that go on the ocean, and a couple of years ago they changed it so that they were not allowed to use I think heavy sulfuric oils anymore to burn because they are very, very dirty. What it turned out is that lead to a lower cloud formation above the oceans, which leads to a lower albe, or it's a word for it. So less reflection of the light on the Earth, so that heated everything up. So actually, we already ran a sort of A/B test on the Earth itself, whether we can affect the climate just by turning on. Are we allowed to use these oil, heavy oils that produce clouds? Yes or no? And it's very hard to, if you only have the observational data, it's very hard to find out that there's like this causal effect, right? So it's because it's also bloody interconnected.
Fair. But yeah, that's thanks for that. That makes a lot of sense for why they wouldn't put it in, because in my opinion, like, this is a very well written paper. So I was like,
yeah.
I was surprised that the authors didn't have this information in there. So yeah, these are just some pro tips over here that they're saying, like, this is how you should approach the problem. Like, I don't think that none of their models are enforcing physical constraints like conservation of mass and energy. So probably trying to put that inductive bias into the model would be good. We actually read a paper recently about forcing a model to like conserve energy. No, that was to minimize energy. Sorry, that was a different paper. But so doing something like that would be useful, taking into account that some of the model, like some of the variables are stochastic versus not stochastic. And then they say that they used a very basic form of normalization. So it'd be interesting to do some better data preprocessing. Let's see. Lastly, they talk about limitations. And I think the only real limitation that they have here, because probably whatever comes out of this research will be useful for other problems related to it. Like, they're saying that one of the limitations is that this data set assumes scale separation, which is, basically it says that convection can be represented as laterally periodic within the grid size of the host simulator and neglects subgrid scale representations of topographic. So maybe I didn't really understand that, but I didn't think about it too much. I was actually thinking that it's because it would just mean like they were assuming that you could treat the physics as local for like cloud formation and stuff. Whereas because when you're discretizing something, you have to create arbitrary boundaries that maybe harm like the accuracy of your calculation. But I think the big limitation that they've pointed out is there's no workflow for, like, say someone creates a new model that outperforms the other ones in terms of these metrics, for you to test your model on the climate simulator that they're using, that they use to collect the data set. And so they're saying it's in our eventual goal to create an API that someone could use to like model to test their model. And I think once that comes out, then we could see a lot of headway in this problem, or something cool could come out of it. Because if they make it easy to evaluate, and on like the actual problem that this data set was created for, then yeah, a lot of things could happen. Who knows? Maybe we'll like apply reinforcement learning to it or something and parallelize it. And the last thing that they say is a limitation is basically that the results, like the models that are being used here, they don't take into account the impact of climate change. So they're assuming like that meaning that if you train a model on this data and then you wouldn't have a way of figuring out whether if you change like the average temperature of the Earth by a couple of degrees, if the model would still be accurate. So you don't know if you can use this to simulate climate change. And that's something we were basically saying it would be great to create a couple of other data sets where you could actually measure like the generalizability to changes in global temperature. So that's the paper, basically about this data set they've created, and a little bit about Earth science. I thought it was quite good. And more than anything, I think, yeah, more than anything, it's just they've contributed a new data set to ML, which is amazing. So that's everything I have to say about that. Not a paper that I feel you can have a ton of discussion about, but I'm happy to answer questions. Yeah. Okay, well, if not, let me just stop recording.